Now let's continue learning about determinants using the method of cofactor expansion. What we just learned in our last video is that we could find the determinant of A by taking A11 times the determinant of A11, and if you'll recall, that just meant take out the first row and first column and then write whatever was left over and find the determinant of that matrix that was left over. So A11 is a submatrix, and that's what we're finding the determinant of. And we also showed the notation that said, hey, if we want to write this as a summation, that would be the summation as j goes from 1 to n, and then -1 to the 1 plus j, and that's going to give us those alternating plus minus signs, and then A1j determinant A1j. So we want to write this a little bit cleaner still, and to do that we're going to use something called the cofactor, and we haven't talked about cofactor before, and yet it's something that is going to look very familiar to us. The cofactor, which we're going to denote Cij, is essentially going to take over the whole plus minus thing that we have going on. That's where that -1 comes in, just like it did here, and all of the determinant part of this. So it's going to essentially replace that part. And what we do is we take -1, and this should be an I, not a 1, -1 to the I plus j, and then the determinant of Aij. Now, what's the difference between what we just did in our last video and what I'm saying to do now? Well, what we just learned always used 1 here. This was a 1. This was a 1. This was a 1. This was a 1. We get the idea. We're only going across the first row. So what I'm telling you is if we're using a cofactor, then I can go essentially across any row or any column, which we'll talk about on the next slide. So what this reduces to says that the determinant of A is A11 C11 plus A12 C12 plus. Now why do I get to use pluses all of the time? Because now I have this -1 to the I plus j, which is going to give me that alternating plus minus that I need. So now let's look at the definition. The determinant of any n by n matrix A can be computed by a cofactor expansion across any row or down any column. So we can go across any row or any column. So previously we were just using the first row every single time. So for instance, if I'm going across the ith row, which is what we just did before, except I was 1, so this was 1, and this was 1, and this was 1, but it doesn't have to be 1 is essentially what we're saying. We can say across the 5th row, well then it'd be 5, 1, and 5, 2, and you get the idea. So I can replace I with any row, or I can go down any column. So it doesn't matter if I'm using a row or a column. So you might be asking, well, Professor Brame, why are you so geeked out about that? Well, because I don't like to do any extra work that I don't want to have to do. I'm kind of lazy. So if I get, say, a 3 by 3 or a 4 by 4 or God forbid a 5 by 5 matrix and I have to find the determinant, then I'm going to find the row or column that makes my work easier or easiest. Let's take a look. Here I have a determinant A, and we already did this in our last video and we found that the determinant was -2. Now when we did this in our last video, we went across row 1 because that's all we knew how to do. But then I'm going to ask, what makes my job the easiest? And what makes my job the easiest is as many zeros as I can get. So I might choose this column, which has 2 zeros, or I might choose this row, which also has 2 zeros. So choose one. I'm going to choose the row since it's the last one I multiplied. So to find the determinant of A, remember what I'm going to do is I'm going to take, and in this case I've chosen row 3. So this is saying A31 and then C31 plus A32, C32, plus A33, C33. And I only have to go to 3 since there are 3 columns, which means A31 is 0. And so I don't even care about this. I don't care about C31 because I'm taking it times 0. A32 is negative 2. And then notice I wrote this down here for you in case you don't quite have it written down or memorized yet. I need to take C32. So C32 says take negative 1 to the I plus j, so that's 3 plus 2. And then determinant, so instead of writing determinant, I'm going to use those straight brackets, of A32. So again, just like we did before, now I'm going to have 1, 0, 2, negative 1. And then I'm going to take plus A33, oops, somehow switched to, that one, fat fingered that one. I switched to a new color. So now A32, or 33 is 0, so it's plus 0. And I don't even care about this part then because I'm taking it times 0. So that's what I mean when I say I'm going to be smart and lazy, is I'm going to try to get as many zeros as possible, because now all I have to do, I've got negative 2, and then I've got negative 1 to the 5th, which we know is negative 1. And then I'm going to take that, whoops, times 1 times negative 1 minus 2 times 0. Oops, I almost wrote 2. That would be horrible. 2 times 0, which is 0. So that gives me negative 2 times negative 1 times negative 1, which gives me negative 2. Now, I had found that to be negative 2 before, but now I've just shown it again in a different way using row 3 instead of row 1. So just for fun, because I know you're having a blast, let's also do this for column 3. So determinant A is going to be A13, C13, plus A23, C23, plus A33, C33. So determinant A, A13 is 0, so again, I'm not going to worry about that. A23 is negative 1, because again, second row, third column. And then I have to come down here, in case we haven't quite memorized it yet, and say, now that's going to be negative 1 to the 2 plus 3, and then the determinant of my matrix 1, 5, 0, negative 2. And then plus A33 is 0. So again, I've chosen one with a lot of zeros. So the determinant of A is going to be, we don't care about the 0, negative 1. And then negative 1 to the 2 plus 3 is negative 1 to the 5th, which is negative 1. Then I'm going to take 1 times negative 2 minus 0 times 5. And again, we see negative 1 times negative 1 times negative 2, which is negative 2. So again, a pretty easy way to do it. I'm going to go ahead and not write that 2 like that. And so I've confirmed it a couple of other ways. Now I could choose any row or any column, but again, be smart about it and choose a row or a column that has a lot of zeros to make your life easier. Here's one for you to try. Choose any row or column that you would like and find the determinant of A. When you are ready, press play to see how you did. So I'm going to choose either column 1 or row 3, because both of those have 2 zeros and I just like to do as little work as possible. I'm actually going to choose row 3 here, and so that would give me the determinant of A is equal to 0 times, we don't care because it's a 0, plus 1 times negative 1 to the, again, this is row 3, column 2, so 3 plus 2. And then the determinant of 4, 3, 0, negative 1. And then plus 0 times we don't care. So that gives me, we are just going to disregard those zeros, 1 times negative 1 to the 5th, which is negative 1, times 4 times negative 1, minus 0 times 3, which gives me 1 times negative 1 times negative 4, which means my determinant is positive 4. Now we're going to do a 4 by 4 matrix, which we haven't done before. Now, if you're feeling up to the challenge, please, by all means, go ahead and try this question on your own. If you'd like, however, feel free to work through this one with me since we've never tried one like this before. So let's take a look. I need to find the determinant. So again, notice it doesn't say find the determinant, but it's given us these straight brackets, and those straight brackets indicate determinant. So when it says compute and then gives you the straight brackets, it's the same as saying find determinant of A. So we'll just call it A for fun. So I'm going to find the determinant, and I'm going to use this column because obviously it's got a lot of zeros in it, and I want to do as little work as possible. So the determinant of A is going to be 2 times negative 1 to the, this is first row, third column, 1 plus 3, and then I'm finding the determinant of what's left over, which is 0, 3, negative 4, negative 5, negative 8, 3, 0, 5, negative 6. And then we can see that as I work my way down the column, that would be plus 0, plus 0, plus 0, and we don't care about what the new matrices would be because we're going to multiply them by 0 anyway. So that's where we are right now. Now, negative 1 to the 1 plus 3 is negative 1 to the 4th, which is positive 1. And then I need to now find the determinant of this. So how do I find the determinant of a 3 by 3? Well, lucky us, we already know how to do that. We're going to choose a row or column, and I'm choosing this column. And that's going to tell me to take 0 times what's left over, which I don't care about that, plus negative 5 times negative 1 to the, that's second row, first column, and then the determinant of what's left over, which is 3, negative 4, 5, negative 6, and then of course plus 0. So I still have my 2 times 1, which is 2 on the outside, and on the inside, I'm going to not worry about the zeros. I have negative 5 times negative 1 to the third, which of course is negative 1. So negative 5, negative 1, and then negative 18 minus negative 20. So I'm going to keep that 2 on the outside for now. I've got negative 5 times negative 1, which is positive 5, and then I have negative 18 plus 20, which is 2. And then if I multiply this, I get 2 times 5, I think I forgot a parenthesis, 2 times 5 times 2, which is 20. So my determinant is, in fact, 20. Let's look at just one more cool theorem. And I'm not going to go through a proof for this theorem, but I'm just going to show you an example that it does in fact work. Before I talk about what's in pink, let's just go ahead and compute based on the way that we just learned how to do it. Let's compute the determinant of this matrix. If I were finding the determinant, I would choose probably this row right here. So the determinant of A would be 0 plus 0 plus negative 2, and then I would take negative 1 to the 3 plus 3, and then the determinant of 1, 2, 0, 4. And it's not necessary for you to put the zeros. I put the 0 because the first term is 0 and the second term is 0. But it's just fine to omit those. So I have negative 2 and then negative 1 to the 6th, which is positive 1. And then I'm going to take 1 times 4, which is 4, minus 0 times 2. And that gives me negative 2 times 4, which is negative 8. So what this theorem, which is theorem 2 in your textbook, what this theorem says is if you have a triangular matrix, which we know a triangular matrix, I'm not talking about reduced row echelon form, but I am talking about anything essentially below that diagonal has to be zeros, and I of course do have a triangular matrix here. This theorem says if A is a triangular matrix, then the determinant of A is a product of the entries on the main diagonal. So what they're saying is I can find the determinant of A by taking 1 times 4 times negative 2. So just multiply those values in the diagonal, which is negative 8, and we just found that it was in fact negative 8. So again, that is not a proof. This is just an example that it works. I'm sure that you can find a proof. Your textbook does not have a proof, but I'm sure you could find a proof if you Googled. I'm not going to go through that with you.